Hi, welcome to another session of Circuits and Networks. In today's class 2 under Basics of Electrical Circuits and Networks, we will be studying about the calculation of inductor, capacitor or resistor when they are connected in series or in parallel. So already we have seen these kind of problems which are pertaining to resistor equivalent, and today we are going to see the same formula how it is applicable for inductor and capacitor. So we'll start with the inductors in series. You can see here we have taken three inductors which are arranged in series, and the combination is given supplied to a voltage source Vs. Then current in series Is remains the same. When the current starts flowing, the voltages will be developed across inductor 1, 2 and 3 respectively as V1, V2 and V3. If at all you want to calculate the voltage across inductor according to the Faraday's law, it is given by VL is equal to L di by dt. With this equation 1, I'm going to make use of this equation in equation 2 such that the voltages which are developed across the inductor through a source can be obtained in this fashion: Vs is equal to V1 plus V2 plus V3, or you can simply apply the Kirchhoff's voltage law in order to get this equation 2. Now based upon this equation 2, when I apply the equation 1 formula, then I will get the total voltage across this combination as LT, that is the inductor across the the voltage developed across the inductor as LT di by dt is equal to V1 is nothing but L1 di by dt, V2 is equal to L2 di by dt, and V3 is L3 di by dt. Because current in the series remains the same, that is why on the left hand side of the equation 2 and 3 and the right hand side of the equation 2 and 3, the value of current, that is di by dt, is same. Hence we are going to get the total inductance value as L1 plus L2 plus L3. Now if at all you concentrate on equation 1, and if we apply integration on both sides of this equation 1, then we'll get the current equation through the inductor as IL of t is equal to 1 by L integration 0 to t VL dt plus IL of 0. It's a constant which can be ignored if the value of the inductor current is initially 0. So from equation 4, IL of 0 denotes the initial current through the inductor, and if it is 0, that is if there is no current, then the equation 1 can be changed to equation 5 in terms of current through the inductor as IL of t is equal to 1 by L integration 0 to t VL dt. So we will make use of this equation 5 for the parallel combination. So when the inductors are in parallel, so this is how the arrangement would be. So here we are taking three inductors which are connected in parallel and given a parallel source as DS. So at this particular node, when you apply KCL, we are going to get IS, that is the input source current, which is be equivalent to I1 plus I2 plus I3. Just remember the formula of the current what we have obtained from the equation 5, that is I of t is equal to 1 by L integration 0 to t v dt, indicating that the voltage in the parallel remains the same. So we'll make use of this KCL equation, that is 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 equal to I1 plus I2 plus I3, and substituting the values for the respective currents in this parallel branches, we are going to get 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus 1 by L3. Since the voltages in parallel remains the same, that is why the left hand side of the equation and the right side of the equation, the integration with respect to the voltage with time will get cancelled, and will remain with the L equivalent formula, that is in the combination of L1, L2, L3 in this way. Or if at all you are particular about two inductors connected in parallel like this, then the L equivalent will be equivalent to L1 L2 by L1 plus L2. Now this formula is quite similar to the formula of the resistors which are connected in parallel. So there it will be R equivalent equal to R1 R2 by R1 plus R2. Also remember, if at all we want to calculate the total energy stored in the inductor, then what would be happening? If at all you apply energy supplied to the inductor, then the formula is given by dE is equal to Li di. and if at all you apply integration, you're going to get E is equal to half Li square. So remember this formula. Once we'll start the solving the problems which are related to energy stored in inductor and capacitor, then we can make use of this formula. Remember this formula, it is very important for the future applications of electronics and electrical engineering. We'll make use of this formula. That is the energy stored in the inductor, which is equal to half Li square. Fine. What about the capacitors? Capacitor when they are connected in series, capacitor when they are connected in parallel. So for this, we'll prepare a tabular column like this. First, we'll see the capacitors in series arrangement. So you can see a voltage source connected to C1, C2, C3 in combined, and current starts flowing in the capacitors. So current remains the same whether it is in series for the inductor or in series for the capacitors or resistors. So here the voltage developed will be equivalent to V1 plus V2 plus V3, and the formula for the capacitor voltage, it is nothing but 1 by C integration IDT. So overall you'll get the value of 1 by C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C3. This formula is quite familiar to the inductors when they are connected in parallel, or resistors when they are connected in parallel. For instance, if at all we take two capacitors in series, we'll get the value of C equivalent equal to C1 C2 by C1 plus C2. And what about the parallel combination? If at all you connect the capacitors in parallel, unlike inductor and resistor, if at all you apply the formula for capacitor current, you're going to get IC is equal to C dV by dt. In fact, when you take this division of Is into the parallel combinations of capacitors, you're going to get I1 plus I2, where you can apply the formula for IC in both the cases, and hence you're going to get the C equivalent will be equivalent to C1 plus C2. Now, what is the conclusion? When you have inductor or resistors, where they are arranged in series or parallel, their formulas are almost similar. Quite opposite to the inductor or resistor, the capacitance formula for series connection and parallel connection is opposite. Also, you should remember that the energy stored in the capacitor will be half CV square. Fine. Let us start with the basic problem of finding the R equivalent across AB. Here you can see uh, there are resistors, the four resistors which are connected in a box, and there is an interconnection between the boxes. So what we will do in order to solve this problem, let us identify the node points. So here you can see I have identified the node points as A, B, C, D. Fortunately, A is connected to C directly and D is connected to B directly. So what is going to happen? Let us redraw this circuit with 4 ohm, which is connected exactly parallel to AB in this fashion. Okay, so 4 ohm is there between A and B. Also, uh, the node points are same, that is C and D, which are connected to A and B respectively. So the node points I am connected with a straight line, since we don't have any resistor or any other parameter like capacitor or inductor, anything like that. So we are connecting the node points which are assumed to be at the same potential. Now estimating the nodes as AC as common and BD as common, and see here between A and B we have 4, also between A and D we have 6. Okay, between C and B we have 5. Again, C is connected to A, that's why 5 is connected parallel to the combination of 4 or combination of 6. And finally 1, which is connected between DC, so D and C, which are nothing but the node points A and B. So now all the resistors are in parallel. So for this we can generate the formula as R 1 by R equivalent equal to 1 by 1 plus 1 by 5 plus 1 by 6 plus 1 by 4. I am simplifying this value as 1 by R equivalent to 1 by 1 will be the value as 1, 1 by 5 is 0.2, 1 by 6 is 0.167, and 1 by 4 is 0.25. In fact, R equivalent would be equivalent to 0.618 ohms. Let us not concentrate on R equivalent problems, because in the past classes we have seen many problems which are related to R equivalent model. Also, we have solved many gate problems related to R equivalent. Let us focus on inductor. For instance, we have find the inductance equivalent, L equivalent between P and Q. The values are given here randomly as 8, 3, 5, 7. If at all you concentrate, 3 and 5 are in parallel and the rest of the circuit is in series. So let us concentrate on 3 and 5 first. So 1 by L equivalent of parallel combination of 3 and 5 leads to L equivalent parallel value as 1.875. Fine. Now this value is in series with 8 and 7. 8 and 7 gives the value addition as 15 plus 1.875. So L equivalent for this total network would be 16.875 henries. I hope you understand this particular calculation. If at all you are good at this, please try to solve the equivalent value of inductors across x and y. You can see here, first we have the parallel combinations of 8, 8 and 4. 8 and 8 will give you the value as 4. 4 and 4 will give you the value as 2. Again here you have 4 and 4, that will be 2. And 3 and 6, again it will give you the value as 2. Overall this series combination will be 6. 6 and 6 will be in parallel, which give you the value as 3. And 3 and 7 are in series, hence the value of L equivalent will be 10 henries. You please comment in the chat box whether you got the same answer or not. Unlike in the case of inductor, if at all there is a requirement of calculation of capacitance equivalent between P and Q, then how do you solve this problem? First you look into the parameters of capacitors. All the capacitors are in microfarads, okay, and see the parallel and series combination. 6 and 4 are in parallel, 14, 10, 1 are in parallel, 2, 3 are in parallel. So first let me calculate these values. 6, 4 gives the value as 10, 14, 10, 1 gives the value as 25, 2 and 3 will give you the value as 5. Fine. Now these three capacitors are in series whose value would be 2.941 microfarads. Now that combination is in parallel with 3 microfarads and the resultant is in combination of series with 3 microfarads. So 3 and 2.941 microfarads which are in parallel, addition of this will give you the answer as 5.941 microfarads. Now that is in series with 3 microfarads, which will give you the value of C equivalent, which will be equal to 1.99 microfarads. Please comment in the chat box whether you got the same answer or not. So that's all for today's class. I hope you like this particular session. Please share among your friends, subscribe to this channel, and please press the bell icon for the future notifications. Thank you.